Hello everyone, welcome to another interesting lecture on fast Fourier transform. In today's lecture, we are going to cover 4-point fast Fourier transform, 4-point FFT, and then we are going to see in general how do we compute the Twiddle or the linear transformation multiplicative W for any point FFT. So for in general, for an M point FFT, how do you compute these Twiddle multiples? Right, so let us take a general example. We start with our 8-point FFT because we have seen this 8-point FFT working in the previous lecture. So for my 8-point FFT, we all know that you have 3 stages, stage 1, stage 2 and stage 3, and let's see how these twiddles operate, or how these twiddles are used in these 3 stages. So at my first stage, I have written from W80 to W87 in sequence. I have 8 multiples, and now using the property, using the Twiddle factors are having your symmetry or your periodicity property. You can apply these 2 properties to these Twiddle factors and simplify them to a whole simpler terms, and that is exactly what I'm planning to do here. So I am taking the lower half of the Twiddle multiples and then I'm writing them as the negative, the anti-symmetry of the top half. That is basically what my simplification leads to, using the properties of your Twiddle factors. After that, we have our next stage, which will be the stage 2 or the intermediate stage. And if you look at the intermediate stage Twiddle factors, they are all, I again have my 8 Twiddle factors or my linear transformation multiple, and they are all in this case multiple of 2, because at stage 2 I'm going to talk about, I'm taking this n by 2, and that's gonna reflect as a multiple of 2. So generally speaking, all the powers are multiplied by 2 when I compare them with the stage on the right hand side. So that can be your stage 3, right? So it doesn't matter, we just say that is your first stage. Now I'm looking at the second stage, and these are the powers which are multiples of 2, and then using the periodicity and the symmetry property, I am simplifying this. So these simplifications have already been shown to you, the steps involved in the simplification, but now I'm here just writing for just for explanation's sake. This simplifies to W80, W82 and minus W80 and minus W82. So all the Twiddle factors or all the linear transformation multiples are either just W80 or W82, it's plus or minus W80 and W82. And your third stage, the multiples are in 4. So I am having the multiples to be 4 for the Twiddle factors, W80, 4, 8, 12, 16, 20, 24 and 28. They are your multiples of 4, and now I have further, I can simplify them a lot more using the properties, and I'm going to just see 2 twiddles, which is W80 and W84, and that is the first stage of simplification, and I again have my W84. I can write it to be minus W80. Alright, so this is how I come up with what are the Twiddle multiples or the linear transformation multiples for each stage for an 8-point FFT. So for an 8-point FFT, I know that I have 3 stages. Then if I'm looking at a 16-point FFT, then I will be writing it from W16 to W16 to the power of 15. Then I'll be having 4 stages. So the second stage will be a multiple of 2, the third stage will be a multiple of 4, and the fourth stage will be your multiple of 8, n by 2, n by 4 and n by 8, so on. So it is something you can do to compute the Twiddle factors, and we are not going beyond 8-point as far as the syllabus for your undergrad school is concerned. We are only interested in the 4-point and the 8-point. So keeping the 4-point as your reference, I'm going to tell you how we can find the 4-point Twiddle factors. So we are going to use the same logical steps that we have followed for the 8-point Twiddle computation. So the same steps means what I do is, the first stage I write my W40 to W43. I have 4 Twiddle multiples, or I have 4 linear transformation multiples, and then I have only two stages, right? Because this is my 4-point FFT. So for my 4-point FFT, I'm going to see only two stages, and those two stages are going to be shown here for your reference. So what are the Twiddle multiples associated with these two stages we are going to see. So at first stage, which where I'm having W4 0, 1, 2, 3, I am simplifying that to be plus or minus W4 0 and plus or minus W4 1. So those are the twiddles for my stage 1. And for my next stage, the twiddles are going to be multiples of 2, right? The powers of the twiddle are going to be multiple of 2. So 0, 2, 4, 6. And then that simplifies. So that is going to simplify to what? So we're going to say, we're going to apply the periodicity and symmetry. So periodicity is very straightforward because it's a 4. So this becomes W40, W42 because the periodicity is 4. Right, so if this is not clear, because if you're watching straight this lecture, this will not be clear. I suggest you watch my DSP lecture on FFT, which is the lectures 14 and 15, and that should explain how I am writing all this, right? So this is very straightforward, and I'm just coming up with these twiddle multiples for my stage 2, which is plus or minus W40. So for my 4-point, now I have my twiddle factors for the first stage to be plus or minus W40, plus or minus W41, and then for my second stage, I'm having plus or minus W40. Done. So now I can proceed to compute the FFT because I know these twiddles. Now I'm going to do the butterfly diagram for my 4-point and then compute the FFT. And the same way I can do the IFFT by taking the complex conjugate and an extra multiple of 1 by 4. Right. So let's get to it. So like what I'm telling is which one you call as your level 1 and level 2, it's totally up to you, right? If you can, because it's your numbering or your labeling. You go from left to right, you call the left one as the 1. You go from right to left, you call the right one as your 1. So it doesn't matter. So let's see this example where my x of n is equal to 1 0 1 0, right? So that is my x of n, and x of 0, x of 1, x of 2, and x of 3. I'm having here, these are the 4 terms. And now for my FFT, I have to arrange. So for my FFT, I have to arrange this in the indexing. The structured indexing for my 4-point is 0, 2, 1, 3. And I'm arranging the signal samples in that manner, 0, 2, 1, 3. And then now let's look at our butterfly. So the first butterfly, the first level is going to be between the successive samples, right? So between the first and the second, and the second stage, it's going to be between every alternate samples. And since we have only 2 stages, we are only, we have to only see that much to get our FFT output. So pretty much that is your 4-point FFT. 4-point FFT is a lot simpler to do it on to do on a pen and paper in your exams, in your objective type service exams or in any kind of entrance exams. But normally we don't, it's like many I have seen more questions on 8-point FFTs. Even though the numbers that that come as the questions, they simplify themselves a lot as you do the computation. All right. So I'm just using scientific calculator to compute what is my twiddle factors for W4, and I'm just let me just do this. Okay, I'm getting it as minus j. All right, so W41 I'm getting it as minus j, and W40 I'm getting it as 1, and I'm calculating that. I did that with the help of MATLAB, right? You can do it with the help of your scientific calculator. Now let us do these things. Let us complete our stage 1 with plus or minus W40, and then let me go to my stage 2 where I'll be using plus or minus W40 and plus or minus W41. Alright, so for the stage 2, my terms are 2 0 0 0 0, right? So the output will be 2 0 0 0, and then I'll be picking every alternate samples, and that will simplify and get you the output. Nice. So that is your 4 points. So I'll let you watch the rest of the calculation steps. So what else is there to say is yeah, one thing you can do here is you can count the number of multiplications and additions. As you can see at the first stage, I have like 4 additions, right? Like I have like two additions and 2 subtractions. So together I can say like I have 4 addition slash subtractions at that first stage, which has which is giving output 2000. And then how many multiplications I have? So I can see again I have 4 multiplications. I have 4 multiplications. So I have 4 additions and 4 multiplications. So that means for my 8 point, I should have had 8 multiplications and 8 additions, right? So let's look at the stage 2. So now let's count how many multiplications and additions I have for my stage 2. Again, I see 4, right? 2 additions, 2 subtractions, and 4 multiplications. So for my stage 2 also, I have 4 multiplications and 4 additions. Alright, so now I have computed the stage 2 and I got the output as 2020, and that is your FFT in sequence x0, x1, x2 and x3. So your output is in sequence because your input is structured, and if your input is structured, your output is in sequence. Right, so it's like vice versa, but I didn't say it in that way. So it just so you know what I meant. So that is how you get your FFT, and then now I'm writing the multiplications and additions here. So I'm writing this little slow because the previous video, the FFT part, at least some of them are telling to go in a slower pace so that it's very they can get more out of this video. If I just run through it, then people are it may not be that useful for my students and other viewers. So I'm just doing it little slow for this FFT. So it is just what I told you. Have 4 multiplications and 4 additions slash subtractions for each of these stages. All right. So now let it be that. For now, I'm going to go to IFFT. So I'm going to do my 4-point inverse fast Fourier transform. And when I say inverse, I'm going to apply the inverse to the output of my previous question. So the output or the FFT of my previous question was 2020. And to do my inverse FFT, what do I need? I need my complex conjugate twiddles. I need my W4 conjugate 0 and W4 conjugate 1, which is going to be plus J. Because W4 1 is minus J, W4 conjugate 1 is going to be plus J. And if you see here, I am not structuring my input. So my inputs are in sequence 0, 1, 2, 3, which means my output is going to be structured, right? And I'm going to do my stages 1 and 2. For stage 1, I'm picking successive samples, and the twiddles are plus or minus W8 conjugate 0, not W8, W4 conjugate 0, since it's a 4-point FFT. So I don't know if I've used W8 anywhere else previously, but it should be all W4. Whenever we are talking about 4-point, all your twiddles are W4. And when I'm talking about 8-point, all your twiddles are W8. So the output that I'm getting is 4000, and that is going to stage 2. And at stage 2, I'm going to pick every alternate samples, and I'm going to do this W4 conjugate 0 and W4 conjugate 1. Then I'm going to get the output, which is going to be ordered or sequenced in X0, X2, X1, X3. Since my input is in sequence, right, the input side is in sequence, the output is not in sequence, and it will be structured, and that will be the output. But that is not all, because we are talking about inverse Fourier transform, and for your inverse Fourier transform, you need to do this 1 by n. So right, we have to do that 1 by n extra, because the formula for inverse Fourier transform says that x is equal to 1 by n wn conjugate x, right? So the x is without the x, if we see, we have that 1 by n into wn conjugate. So I have done the w conjugate, I have done the w4 conjugate part, I have integrated that into my butterfly computation, but I'm still left with that 1 by n, which is what I'm going to do next, and that will convert my output 4040 into 1010. right? And when I do that, I get 1 0 1 0, and this is not in sequence. So this is x0, x2, x1, and x3. So this inverse FFT output is given in the structured indexing, and then that is your output. So this I'm writing here. When I do the IFFT, I am going to get what? X0, x2. Okay, so now I'm going to structure it. So that will be the same x0, x1, x2, x3. I have not written, but yeah, so it is understood. Okay, so now the multiplications is again 4 plus 4, and your additions is 4 plus 4. Okay, so that I could have left a remark there because this is x0, x2, x. Okay, fine. Just remember that. So now let's come to the computational complexity of your FFTs. So the number of multiplications and your additions for your FFT is going to be what? So we have used this FFT only for the sole purpose of saving up on our multipliers and adders. So if you're building a hardware and you're building a hardware with these multipliers and adders, and then what happens is your multipliers and adders take up a lot of this infrastructure, and if they have plenty of computations, then it's not very ideal to have many multipliers and adders. So the optimization, so what a single word is optimization. So now what will happen is in your FFT, your multipliers and adders are getting optimized better. So that is the idea that we were telling. So now for your 4 points, right, when n is equal to 4, I had what is the total number of multiplications and additions. I had, you can say, like 8 additions and 8 multiplications. For each stage, it was 4 and 4. So 4 plus 4, if you go back to a slide, you can see 4 plus 4, 8, and 4 plus 4, 8. And that, if represented as a formula, I can write it as n log 2n. So that is your FFT's number of multiplications and additions, and that is comparatively simpler or comparatively more efficient, because your original DFT was having the number of multiplications to be n square and your number of additions to be n square minus n. So which means compared to that, your n log 2n is lot efficient. So if you take for 4 point, you're gonna get n square, so that's gonna take 16 multiplications. But here on your FFT side, you're having only 8 multiplications. And as the n goes up, so you see a case where you have 256 point, so then 256 square, that is big, right, compared to 258 log, n log 2n will be 256 log 2, 256. That's going to be just 8 into 256. So that will be much smaller. So that's why your FFT is what is primarily used in many of the, not in many, in all places. So wherever you see Fourier in your DSP processors or in your FPGAs or in your VLSI boards, all are based on FFTs. So which FFT, maybe there are some variations, but they have used one or the other form of FFT algorithms in their computation. Now let's finish this lecture with a small a small textbook computational complexity. So why I wanted to bring this is, when I was going through some of the textbooks like Procus and Oppenheim, I saw that there is something called as n by 2 log 2n. So this multiplications is what is given in your textbook, and I have just written previously, I've written it as n log 2n, right? I've written it as n log 2n as the number of multiplications. So why this discrepancy? Why it is given as n by 2 log 2n in your textbook, and we have counted it to be n log 2n? That is mainly because if you take your Twiddle factor, right, the Twiddle factor is multiplying, it's like the plus or minus, and it is multiplying, the multiplication is the same. If you see, the Twiddle factor is a plus or minus something, I can write W40 into B. So this is what we are having W4 and W8B, right? I am writing an example, but if you see here, the plus and minus is counted as 2 addition slash subtraction, but your W40 into B, that multiplication is just done once because I don't have to do it twice. I can do it twice, but that would be just repeating the same, and we are not allowing for any repetition. So when it comes to efficiency and optimization, repetition is something, repetition is our kryptonite. So we don't want any repetitions or redundancies in your additions and subtractions. Right. So in order to keep away from those repetitions, your W40 into B is just one multiplication. And if I go about with that calculation, then I'm gonna count to only 4 multiplications. Now where I counted 8, now I will be having only 4, and that is why you have that n by 2 log 2n in your textbook. Good. So I am sure with this, I know with this we are, I think we are finishing with DIT. Mostly, we are completing on DIT FFT. So we have one more lecture on DIF, decimation in frequency. So we'll see that for the next lecture. Thank you for listening. Have a good one. Bye.